today's problem set. Today we are going to use another approach to compute our posterior. So the idea here is, okay, we have some prior, we observe some data, that's our likelihood, we figure out some posterior information. And what we did yesterday was called a grid approximation. We basically try to evaluate the likelihood, the prior and the posterior at each possible value of the theta. So when we are working on low dimensional problems, like theta is easy to define, right? Like if it's a bag of balls, like your limit number of configurations. If we are dealing with one free parameter, what the true x value is, we build a grid for x. We have two free parameters, the slope and the intercept. We build a two-dimensional grid for the M and D. But now if you're moving on to higher dimensional problems, say we have 100 free parameters or even 1,000 free parameters, that can easily happen when we are dealing with the real actual physics problems. Like we are sampling, we are learning the population statistics of a sample of 500 exoplanets. Each planet has two free parameters, and even a third one that we don't really know the exact uncertainty is. So that would be, you can quickly reach to thousands of free parameters. In that sense, it's almost impossible to do this grid approximation. And we need some algorithm that is much more efficient to sample, to approximate this posterior. And that is called Markov to Monte Carlo. We are going to redo the draw balls out of bag problem again, but using the Markov to Monte Carlo way. So again, we have a bag of four balls. There are like some black balls, some white balls. We don't know how many there are for each can. And we make an observation, and we want to understand the posterior at the time. So what we could do instead is have a small robot to sample the theta space. Our theta here, 5 different states, and we have a sampler, the small robot, to explore this parameter space, and we count like how many times the robot visits at each state. And the idea here is we want the number of visits per state is proportional to our posterior. So if you remember the posterior we derived for a bag of 4 balls, draw a black ball, that would be 0, 0.1, 0.2, 0.3, 0.4. If we are making 100 visits, like this robot will explore the space 100 times, we want to counter to be something like 0, 10, 20, 30, 40. So the number of visits per state is proportional to the posterior distribution. That's what we want to achieve. And let me propose one way to achieve this. We begin with a random state. Let's just call here and just begin with state 3. And I calculate the unnormalized posterior one. So it's just the likelihood times the prior. That's the similar function for massive posterior, but it's not normalized. We just interested in the posterior at that certain state. And then we flip a coin. If the coin is a head, then we move one step, like once we move to I plus 1 state. Propose to move on I plus 1 state. If it's a tail, we propose to move to I minus 1 state. We calculate the unnormalized posterior, the capital P again, as its proposed state. And if our proposed state has a higher probability than the previous state, we accept its proposal and we move to that state. And our counter of the state as well. So for now, say I flip a coin, it's hat. So the proposed state is like, okay, proposed to move to theta equal to the state number 4. And I calculate the unnormalized posterior at that point. So if you remember that this should be 0.4, this is 0.3. So I compare 0.4 to 0.3. This proposed state has a higher posterior. Let's move to this state. And if on the other hand, I flip coin, I got the tail. Now instead of like the proposed state, instead of being here, it's going to be here. And we can calculate the posterior again as a new proposed state. That would be 0.2. I compare 0.2 to 0.3. Okay, now it's at this L state, at this L statement. They don't reject the proposal just because it has a slightly lower probability ratio. We accept it as the ratio of this proposed state divided by the current state. So in this case, 0.3, 0.2, that's like, okay, as a 66%, we accept the proposal. Yeah, go ahead.
Why do you choose that ratio for the probability?
Right. So the idea is we want to make visits, and we want the relative number of visits is proportional to the relative ratio of the posterior between two states. So in that sense, like we need to take the ratio to be the posterior ratio between the two states when they decide to visit or not.
Is it, okay, I'm just curious if it's lower already.
So, right, if it's lower already, we just don't visit that. If we are really aggressive, always want to visit the highest probability states. We just move from here to here to here, and then our robot just stuck at here. It finishes exploration. Okay. So we want some algorithm to be able to represent the relative ratio between every like two states next to each other. So that's why, like, okay, even though this proposed state has slightly lower posterior, we still accept it as a ratio. And that ratio is determined by the relative ratio of two states, the posterior of that. So, okay, if it's +1 case, make a proposal, we calculate the posterior, okay, it's higher, we move to the new state, and the counter increase 1. And we flip the coin again, another height, we move to this higher probability state again. And the idea is we can do this sort of exploration in time. You will code 1 in 20 minutes. If I'm doing 10 explorations, that would be how it looks like. So it's a small number. My after I reach to this state, just stuck here, like, yeah. I keep rolling that, It keeps, I keep flip coin. It keeps giving me a +1, +1. And this one, if it's +1 for state 5, it just go back to state 1. And the posterior state 1 is 0. So, okay, it never moves to there. It just stuck somewhere here. Finally, we have done, we got the tail that allows us like to move back at some relative probability. So a small number, they couldn't really present the posterior distribution. If you increase number to 100, you're slightly closer. If you remember the result from yesterday, it should be a straight line, right? And a southern tail. For southern trails, it's much closer. And I should also know that when we reject the proposal, we just stay as a term state, and our counter is increased 1 as well. Any questions? So what the process I was talking about is the Markov chain multiple. And the process of random sampling, like any sort of random precise to approximate a number that is Monte Carlo precise. And when they make proposals for next state, they only care about the current state. That sort of chain, like one to another state, this sort of chain is called the Markov chain. So yeah, the whole philosophy here is, I've said again, we want to have the number of visits to each possible state is proportional to the posterior probability. Okay, so what is very important in this MCMC algorithm is the alpha, the proposal acceptance rate. In our example, we look at the ratio of the posteriors between the proposed state to the current state. Right. So if this metropolis parameter is greater than 1, we always accept a proposal. If it is less than 1, we accept a proposal at that ratio. That's the metropolis algorithm. And you may heard about metropolis 15 a lot. In our flip a coin example, this 15 part is just equal to 1. So Q here is a proposal kernel. A proposal kernel to move from some current state B to a proposed state A. So in our sense, we flip a coin. So from state 3 to 4, that's 0.5. From the state 3 to Q, that's 0.5 XL. So in that sense, this Q kernel is symmetric. So lower one, Q of state 4 given state 3, that's 0.5. Upper one, Q state 0.4 given 0.3. Q state 4 given state 3, that's 0.5 as well. So this ratio is symmetric, like the proposal is symmetric. So this ratio equals 1 in our flip a coin. So in that sense, okay, our acceptance rate, we could just look at this metropolis part, right? So for our flip a coin scenario, we just have this metropolis algorithm.
So in this case, the probability of moving to, okay.
Yeah, exactly. So yeah, that's like a 10,000 trail, what it looks like, just like infinite, approximate to a straight line. Now let's think of this Hastings parameter a little bit harder. We have an example I showed, we have an unbiased point. So when we flip it, it gives us equal number, it has equal chance of giving us a -1 and or a +1. Head and tail is like just a bias. If we instead have a biased coin, so you can think of it as a dice or a biased coin, it gives us more heads than tails at a factor of 2. So like it's randomly drawn from like -1, -1, +1, +1, +1. So now the proposal is a number randomly drawn from this options. We have more higher probability to get a +1 than a -1. When we use this proposal kernel to estimate the posterior, we are very much biased towards like higher states. That's when the Hastings parameter getting important. If you look back to this Hastings again, now our proposal from state 3 to state 4 is not equal to state 4 to state 3. State 3 to state 4 is a factor of 2 higher than moving from state 4 to state 3. So when they calculate these acceptance rates, we want to like have that Hastings parameter here to do some sort of renormalization to cancel out the bias out of these proposal kernel. If they do that, it goes back to 3 lines. So yeah.
I'm just confused by the wording.
Mhm.
The slide before. Oh, where you choose the proposal kernel?
Right.
Yeah, so for choose the proposal kernel, then there's a ratio correction bias.
Oh, the ratio is now like B given A, it's the ratio of the Q in denominator to the Q numerator. Does it make sense? So, for example, the proposed state is 4, our current state is 3. Then for a bias cooling example, we show the Q upper will be 1/3, the Q lower will be 2/3. And the ratio of the two is 1/2, that's 0.5. Yeah,
Okay.
that's a ratio. Yeah.
You're just saying, okay, this ratio is composed of 2 proposal kernels.
This ratio is a ratio. When you
It seems like you're free to choose the kernel. So
Uh-huh.
yeah, you can just use the unbiased point set and you don't have to do this.
Right.
And
So
if you choose the biased one, you have to do this. Why I would choose the biased one?
right. So in reality, what we usually do, okay, we just go through a random Gaussian random walk. In that sense, okay, we make this proposal out of a uniform distribution or some sort of normal distribution, and it's totally symmetric. So that's like what people do in most cases. But there are different science questions where we are actually driven, we have like some sort of specific proposal kernels that is not symmetric. For example, a skewed Gaussian, you want to have the value, like force it to some value instead of making proposed as a normal Gaussian. There are special cases like can search for like proposal kernels, they have different shapes, and if it's symmetric, it's just like okay. When it's asymmetric, just make sure we need to correct for this case.
But if you're correcting for the bias, then what's the point of using a biased kernel in the first place?
Right. So, like for example, I have a parameter of interest that is forced to be being greater than 0. So we are making proposals. For example, at state x equal to 1, we couldn't really move a step 2 to x equals -1, since like the x is bounded from 0 to infinity, stuff like that. In that sense, like the kernel is not symmetric anymore. There are like real cases that we are forced to use an asymmetric kernel, or sometimes we have some reason to use asymmetric. Yeah, thanks. Yeah.
But it also means that we very prior dependent. So like ACMC would be like very prior dependent. But like essentially we don't know nothing. We don't know anything about our parameters.
Right. Right.
So we have to like, how do we choose the best prior?
Right. So yeah, in that sense, like the prior is uses annualized posterior, right? So when they choose a prior, we just use our best educated guess of it. And if we have no prior information on some parameter, we just try to use as uninformative, as unbiased prior as possible. And it's all written into this normalized posterior. This one is like we already have the likelihood times the prior. So the prior is you still need to define some sort of prior.
Yeah, but if our prior is wrong, will we like converge to better? Like we might, there's a chance that we'll not converge to
if your prior is totally wrong, like, and it's super text, and like red is not going to lead us to like the correct. I mean, like, no, there's like no right or incorrect. There's no correct or incorrect answer. It's just if you do trust your prior is super tightly constrained prior, even though your data doesn't really super agree with that prior, your posterior is still strongly affected by that prior. That's like the choice you make. So yeah, hope that helps a little bit. Yep. So that's the part one. What I want you to do next is to spend like 20 to half an hour on writing this metropolis sampling algorithm itself. If you look at the notebook, so today we have like 2 notebooks. Ryan, are those like on the main LSST?
Yeah, they should be there. You pull the request, you make it all and upload it.
So in this folder, if you are interested in like reading more about the play, look at this PDF, MCMC, and the example, the notebooks we want to work on now is the sampling. Random walk, and that's what it's doing here. It is exploring the space pretty well. It's pointing to the high probability regions, but it's limited by some time step. Like you couldn't really like start from one point, you make a proposal, you explore another data point, also high probability, but very much uncorrelated from the current one. So another way, a smarter way, or the most commonly used way to make proposals nowadays is this Hamiltonian Monte Carlo algorithm. So we still have our log posterior space. Now I just visualize it from 2D to 3D, right? So the color is the same, and we are plotting the log property in Z-axis. This becomes a 3-dimensional some sort of potential. If it makes it the opposite, okay, that's a potential map. So what we want to do is to sample this posterior distribution as some sort of potential. And that's the idea of Hamiltonian Monte Carlo. This system, the log likelihood, is described as some sort of canonical system, e to the negative likelihood. You have data points explored the lower energy state more often compared to the higher energy state. So we just have we have a goal that explores this parameter space. We begin with some randomization, and let's have a random momentum cake on this ball, and that will be a vector depending on the number of free parameters. We have 2 now. That will be a vector of the size of 2 with some momentum in both M and D direction. So okay. We have some initial momentum, we have some position. Let's integrate the system for a certain time interval, delta t. And the ball will just follow the curvature of this potential. That's like, okay, when you calculate the acceleration, that's the gradient of the potential relative to the position. That's the acceleration. So we are beginning with some initial velocity that is from a random draw, and we integrate the track, we integrate the ball like a move in the field for some delta. See, we begin with the proposed region here, and we have some initial random momentum that is pointing to like negative negative B, like a momentum somewhere near here. And the ball will just follow the curvature of this potential map, just move from here to here. That's one proposal. Does it make sense? We just integrate the track of this ball from this potential map, and this potential map is just the negative log likelihood of the posterior. So in this sense, if we do this trail infinite number of times, it will always represent the number of visits at each location. Will always represent the posterior distribution. And also, like, almost always time we accept the proposal. We just like, okay, integrate the ball to with some random initial momentum to a new position. In rare cases where we don't accept the proposal, that's when the whole system, the energy is no longer conserved. So what we are doing, we don't really know the exact trajectory of this ball on this potential map. What we need to do is to calculate the curvature, that's the partial gradient of this, let's call this log PS, negative log posterior as U. We need to calculate this partial U, partial X, partial Y, like partial theta for each thing. So we need to do that differential, we need to calculate the differential value to let this ball move some of those potential map. So in most cases, a leapfrog algorithm is using, that's a symplectic integrator. You may have heard of that, like from when you are doing embodied simulations or things like that. A symplectic integrator is is benefiting from symmetric proposals in Hamiltonian system, in which means like the energy and the momentum is best conserved. So that's why we are using a leapfrog integrator. So, but if the curvature, here we are like using like the posterior map is really easy shape. If it has some really sharp gradient, then we don't always like find the exact trajectory of the ball. In that sense, the resulting energy after the proposal is actually off from the original, from the energy at the initial state. In that sense, we reject the proposal if it's off by a huge amount. That's like the metropolis part convection. So that's like a more mathematical description on the Hamiltonian system. If you are interested in learning more about it, there are like tons of resources online. What we are going to do here is just borrow the smart algorithm from a probability modeling package called PyC. It has all be written for you. And what we need to do is to learn to program in that language. And PyC is now one of the most commonly used probability programming language in astronomy, in my opinion, and bias and the actual quantum science. So let's just like take a look at PyC, and we will work on the examples, line fitting in PyC again. And we will work on a real astrophysics example after that. So the syntax for PyC is very straightforward. You can almost build every model you need in 20 lines. What you need to tell the PyC is what your prior are and what your likelihood is. And then you let the PyC do the sampling. That's it. Yeah. So the momentum. Right, how do we determine the momentum? Is that a question from a proposal? The momentum is just a random draw from a normal distribution, the size of the number of free prime. So for this time C model, we begin with define some priors. For example, here I'm modeling a normal distribution. Our prior are mu and sigma, mu and SC I'm using here. And they tell the time C what is a distribution of this random variable. PM dot normal, that's like a normal distribution. If you go to the time C syntax, it has like 20 to 50 like tens of like distributions you could use for the random variable distributions. And you need to gauge this parameter a name, that's mu here. And those two doesn't have to look the same. You could have like mu, PM normal, X, like whatever you want to name it. That's like just something you can make up. It's usually helpful to just have your mu and this script name to be the same. And then you tell this, you subscribe the location, the mu of this distribution, mu equal to 1, the variance, the uncertainty is just sigma equal to 0.1. And the last piece, the init value, this is optional. Some of the optimizers require to give an init value. But like when we are running MCMC, it's not really required. And then, okay, we can do the same for SC, another parameter of interest. And for the uncertainty, we want it to be always to be positive. And we can borrow another distribution from HC. This is like half normal in this case. And they tell, okay, what the sigma is. So that's a prior step. So each time C model, you have like 2 steps. Write down the prior, the second step, write down the likelihood. You guess, okay, so when we have like Gaussian uncertainties, the IC is now model parameter mu, the mu from the prior, and we have some data to observe. So this observed in fitting line example, this observed value is like Y observed. This mu value is like Y true, and the sigma is the uncertainty we are having. So write down the likelihood. In Pansy, the default is a log likelihood. And it's smart enough that like if your observed data is a vector, it's just automatically add up all the likelihood together for each data point. So that's our model. That's it. Like you write down those 3 lines, you finish building this Pansy model. And with this model, we do some PM sample. In default, like we have like tune for 1,000 steps, we just, okay, the MCMC has some initial exploration where the trails doesn't really represent the true posterior parameter space. We just down those initial starting stage, so warm up stage. And draws, like how many draws we make after the tunes. And target set, like this is like when I was talking about like when our potential the U have a sharp gradient. Sometimes we have inaccurate calculation on the energy, the total energy is not conserved. So we like the code to bridge to some target set. And the higher the value, so if it's a very complicated posterior distribution, we may have to make the target set higher so that the energy is conserved. So you can think of this as like what fraction the total energy deviates from the proposed one compared to the initial. And there are some default values for each of those. When they don't tell the time series what to use, we just say PM.sample. Let's say in default, if we use 1,000 tune sets, 1,000 draws, and target set, in default is 28. So let's say for the time series model, and you are going to work on this for the frequency line example. So install those two packages if you don't have that yet. Open terminal and active your countdown environment for the LSST session, and make sure you have those two packages.
Yeah, like, oh, we can't. What?
Like contraception hard time. Solving the so what is the
After you have those two packages installed, you can open the timec.apply notebook on the GitHub repository again, and make sure you can run the first two cells appropriately, or like the first cell, like if you don't have the PDF effect. And you could start working on the example for the frequency line. So for the frequency line example, I basically gave you all the components we need for this time-series model. This is just having a better sense on like what this time-series model is doing, and can plot trace the posterior, the trace plot, the corner plot, to see like, okay, how well your posterior is being sampled. And for the rest of the section, I like you to work on this mass-radius relation for small exoplanet. So if everything works well in next half hour or so, you will reproduce some science paper results published 10 days ago. And your analysis will be better than the one in the paper.
Oh.
So yeah, let's just like get started and work on this stuff.
are you doing here? Yeah, it's not. done trying, but it's struggling. Oh, it finally is like, okay, that's incredible. It just took a long time. Is yours working? Mine's solved, but it's claiming that it doesn't, this class doesn't implement the answer at this. That's a critical component of the context manager. Did you also do the Python graph viz? Yeah, that one is installed, no issue. Like Jeff model equals GM dot model course correct. That prints out. Or is that right? Yeah. So it has an event, but let me know when yours is. Yeah, it's taking its time. Oh, here we go. Let's see if I can import it. Python graph. What? What's in yours? Let me go back. Oh. I think someone else is going to do the same thing. So let's see. So mine imports. Oh, somehow it didn't do it. I will now on the null part. Here we go. One more. Yeah. It's weird that yours is breaking in that way. Yeah. Someone with exactly the CIERA. Yeah, I except their attribute error is now exit. So mine doesn't implement enter, theirs doesn't implement exit.
What's this?
So
The answer.
Yeah,
But back to the same.
What?
that's what I am right now. Even though I just updated IMC.
Well, you know, it's like doing the environment. Like, it's trying to like make to download the right version of all the other packages you have, like with all their dependencies. So it could have done one that's like
What if I just
kind of lame.
let me see if I pip install it? Maybe because pip usually has the list most up to date thing. Let's hope.
Oh no.
Cross.
Import error.
Not be correct. So it takes a while for sometimes to find the highest. So find is steps.
So, yeah, that's like the most tricky part. The rest could be are somewhat straightforward. And why we are using a log A, log B instead of A and B? When we are using a log uniform distribution, we have a much more well sampled for small values. So if we the slope or the scaling is actually 0.03, we are using a uniform distribution, it won't be able to present that value. Whereas if you are using a log, it is doing a good job. A log uniform, it could do a good job. And okay, so how do we describe the posteriors? What I prefer to do is just make draws. We have A and B posteriors. We calculate what would be the expected mass radius relation for each A and B pairs from the posterior. And we plot those lines in those gray lines. And we use some certain alphas, and you can see, okay, the region the higher draws is the lines with higher probability is just getting darker. So I feel like draws is more robust than you are plotting lines with some confidence interval or credible interval, since that won't correctly represent the shape of the line you are having. And then, okay, for the both water and rocky water planets, you can clearly see two populations. The darker color are the rocky ones, the planets with composition similar to the Earth, and the orangish ones are water wars, like 15% Earth plus 50% water. And what we are doing here is, okay, we don't know like what fraction, we don't know which system like is belong to which world. So a certain planet could be both a rocky, it could either be a rocky world or a water world, and or the solutions degenerate, it could be like probably like some component of both. So in this case, what we are using here, P is a Dirichlet distribution. That tells like what fraction we have for each possible world. So now we have a set of two, water, rocky and water, and the sum of the P, the sum of the two equal to 0. So let's see, if P is, we have 60% of rocky, 40% water, then this P distribution will be like 0.6, 0.4. And then the category data would be like which category we are talking about. The Z would be 0 and 1. 0 is the rocky world, 1 is the water world. So those are like some information. Those are actually hyper priors. So you'll learn more about that tomorrow. when you're studying the hierarchical model, but here's like a sense of that. Those are priors, hyperpriors. We are using any information. We don't prefer like more rocky words than water words or more water words than rocky words. We just like the data to figure it out. So what we get by the end of this, we get, okay, the fraction systems that are rocky words and the fraction, one minus that, the fraction of that are rocky words. And we know like which category the planets belong to, either rocky or a water planet. And then the trick here is, since we now have like two power laws, like which power law we use for like each planet. This C parameter has a shape for the lines of the planet. Each planet has its C, and our A and B has a shape of two that's like for rocky and waterworks population. And AZ would be, okay, the A for that population. It's like A bracket Z equal to 0, that's the scaling factor for the rocky words. B bracket Z equal to 0, that's the power law for the rocky words. Each planet has its own Z, it defines which population is belong to, and we have A and B from this shape of two for those two types of words. And you can sample that, and there's some divergence. This is because this problem is a complete problem. And one way to deal with this divergence is to instead, we can do some sort of transformation on both A and B. So this is a trick you can use when you do NumPy. When you do PyMC random variables, you can transfer this variable. For example, here now, I force the log A and log B to be ordered. So if I don't make this ordered, then like, okay, the A and B fraction could swap each other, right? Like the fraction P also could swap each other. The parameters are also like, so the data will just be degenerate. We have, now we force the A and B to be ordered. In that sense, we also expect the order to be A and B to be ordered for rocky and water words. Like the density for water words would be slightly lower. The power law would be lower as well, since like now the equation of the state of the whole planet is getting like 1 over that is getting like it's getting smaller. So it's like at a certain m you expect a larger radii for the water words compared to the earth. So we do have like some informative understanding on A and B, and we can like make this older. And if you run this again, you will see much less divergence. Here, I'm only making A to be older. If you can also make B as older, and you could increase number of steps. You could increase the target step rate. That will all help dealing the divergence. But luckily, like here, like the divergence doesn't really affect our answer that much. We are getting the blue ones are A and B for the rocky words, and the orange ones are A and B for the water words. And we are even getting the fraction of those, like 60–70% of the planets are rocky words, and 30% are water words. So if our sample is complete, then we have an understanding on like what are the types of small planets that are having around Angeles.
I'm reading into this, but can you say what the black lines are?
Yeah, the black lines are divergent. It's, yeah.
So if they weren't there, they would be outlining the shape, the curve. So what does it mean that it's a divergence?
Right. So it's like at certain position, at certain number, at certain chin, like we random walker, right? When they reach to, so there's our stats. When it comes to like public stats, 300. At there, like okay, we are calculating the gradient of this log likely posterior the gradient is really sharp, it's not really well described. The result, the sample from the next step is like the energy is totally off. That's where divergence is happening, and to do that, we can increase the target factors that will help with better solve the gradient and to avoid this divergence. Yeah.
Two questions. Once the divergence happens, what does the chain stop, or does it restart?
It just goes back to the divergence happens when you're, for example, your partial differential, you according to theta gets to like really large number, and it just like go back to the previous step. It's not really stop the chain. Yeah.
Okay, and then do you, when you're actually producing papers, do you ensure that you never have divergence, or are you okay accepting some divergence over the course of running many chains?
Right. For complicated problems, especially hierarchical problems, you usually have divergences because it's really hard to solve. And if it's a small fraction, then I'm okay with it. Yeah. So we can also plot this C. This C is the capture data for each planet, and now I'm plotting the first 20 of those. And you can see 0 is rocky worlds, 1 is water worlds. And the first planet is like rocky worlds, and 21 like symmetry are rocky worlds, but it has some of these worlds. So you see the posterior distribution for each of the planets. And for most of them it's easy to figure out like which population it belongs to, but like there are some that it's really hard to distinguish them from the rocky and water worlds. So that's it, and you can plot this here. Those are the matrix relation for rocky worlds and water worlds for planets around M dwarfs. That's yeah, how you reproduce the result from the science. And there's abundance problem. You can try three population distribution to include the path world. But like for passive planets, if you look at the matrix relation, this passive planet is pretty much, the radius of them is pretty much independent of their mass. This is because they have like a few percent of hydrogen and helium atmosphere envelope, and that could really change the size of the planet, but it's only like a few percent of their mass, so the mass doesn't really change so much. So it may not be ideal to describe them as the power law again, but it's something you could try and see what you find. So that's it. Happy to answer any questions like during the rest of the day. I will be here to Friday.
So we have a few more minutes before the lunch break, so if there's no questions, let's work for another 15-ish to 20 minutes, and then we'll break for lunch.